Awesome. Okay. So, hello, everybody. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device. Here for specific, so it's QiML, or quantum-inspired machine learning algorithms for medical R&D applications. So this is discussion 102, September 28th. So the chart that you're looking at right here is all of the different QiML applications out there. Now, dequantized algorithms are basically if you have something quantum algorithm, you turn it into classical. However, there's not that many of them. Tensor networks, we'll mostly be going over this quantum variational algorithm simulation, so QSVMs, QCNNs, and so forth. So I wanted to do an introduction here to this all, and I briefly touched on dequantized. It's helpful if we can get to these. You wouldn't need a quantum simulator, and it's basically you're learning, how to get these better algorithms through quantum, and then just run a classical algorithm that's analogous to it. And so the level of quantum at that point, there's no more quantum, but with similar performance. So you'll probably be hearing more about dequantized algorithms, but we're going to focus more towards the VQCs on this side. So this is if you have a quantum algorithm and, you're basically wanting to use it on a quantum simulator. We'll have time for questions in a little bit here as well. Now, this is actually considered CC. So if you've seen this chart before, this is common from, it's the big table of quantum artificial intelligence, going back to the 90s when they did, quantum algorithm research. And since the quantum algorithm is being processed on the data generating system is CPU, and the data processing device is also classical, we're in this upper left-hand corner called CC, for quantum inspired machine learning. And that's where a lot of, different experts and especially big companies, and national labs are using this because you can take advantage of the algorithm with the advantages of differentiation, how we see it, how we know it from classical. Any questions at this point? I see. So Rishik, did you have a question?
Yeah. Hey, hi, Kevin. This is Suraj. Rishik is my son's name. So anyway, first off, thank you for hosting this. The quick question I had, so if I heard it right, so the dequantized algorithms are quantum algorithms interpreted in the classical notion. Is that the way to understand that,
Yeah,
or is it just
it's
the
mostly
classical
if
control?
you want to prove that your quantum algorithm really has advantage, you convert it, you dequantize it, and then if they
Gotcha.
have similar performance, then that's the case, is that you've dequantized the quantum algorithm. So there's
Okay.
advantages with it, with doing that method. It's just on these charts that the author showed for this paper, there's not many out there, meaning that
Mhm.
it's harder to do as opposed to, the amount of research that's being done, with a quantum circuit simulator, these types of things.
Okay.
Awesome.
Thank you. Yeah.
So I'm going to start off, and I organized this by disease type. So this is COVID, and if you've run a lot of these demos before, so say for instance Penny Lane demos, this graphic on the left should be very familiar. This is the convolutional neural network demo that Penny Lane put out. So its stock is 4 qubits. So when I count 4 qubits, it's 1, 2, 3, 4, like that. And this is a specific approach of using a quantum algorithm. So your measurements, go into output features like so. And the one on the right is, their proposed model. So they're saying they're using these RY rotational gates as the embedding. So you have to get this straight. Like if you're coming from deep learning, so embedding layer, variational layer to measurements, and then so the unitary matrix is often, this variational circuit that you can train these quantum parameters, and this is what makes it quantum machine learning inside the unitary matrix. They don't have to be trainable. C0 gates or entangling gates or CZs are typically not trainable, but something like an RY gate and RZs and RXs, these are trainable. So you get these output features here, and then, so here's the algorithm they show. And I think this is it's either a template or it's a basic design that they use. Now, when you use things like Penny Lane, and also Qiskit has templates too, or they might call them ansatz, is that you have a whole range. Now, for anybody that's done this before, it's tricky to get your variational algorithm right, but it's essential that the embedding is correct. So I've done studies that prove this, that even with just embedding, you can get really good results, but to go to that next echelon, like testing number of layers, like numbers, of increasing the depth of your quantum circuit, some don't work well and some do. So I think a lot of people give up hope on these variational circuits, but they typically take a little bit more time, especially if your data sets are bigger. So they showed this in specific, and I've read this paper before, I believe. It's just, this figure 4 execution block diagram of ML versus QML. What they're showing is their method, they're saying on the right hand is more of this serial method as opposed to this, parallel method, or maybe a little bit more intricate for classical before. So the thing to keep in mind with all these is it's really important to read these types of papers, even though we all kind of know where things are at, like, getting a little bit better performance with the quantum algorithm is going to cost you with, speed and RAM typically. So this was performed. So this is quantum algorithm for quicker clinical prognostic analysis. A lot of these were like during, this time period, 2000, especially 2021, you'll see these COVID QiML papers. And I think even going to 2022 as well. So they said they were able to get an average accuracy gain of a 2.9% gain out of this, and then with an average recall of around 97.7. So, it's important with a lot of these. Was there another question? So who do we have up here? So Suraj, did you have a question?
Yes. So the statement on the right is pretty fascinating in terms of the improvement in gain and the average recall as well. The question I had is around the data sets, right? Was the amount of data used the same or similar, or are we in a state to say that while using the quantum networks, we can potentially get the same amount of gain and recall with lesser amount of data? Because I've been working in the medical field. One of the challenges getting the data in the medical field outside of your open source data sources, right? Especially when working on audio visual kind of applications, is data is hard to come by. Okay, so has it been proven that QML mechanisms can achieve the same amount of precision when compared to the classical approach using potentially lesser amount of data? If
Yeah,
we are at if we are at that stage, then it's definitely a big breakthrough,
it's harder to
especially for
prove
medical
because,
field. Yeah.
say for instance, I've been working on a quantum transfer learning model, and it's based off of a classical model, but there's just inherent differences between the image pre-processing, some of these things.
Mm-hmm.
So, myself and other researchers, we just have to be careful because we can optimize it to the point where it's just like, okay, we did that for quantum, and then could classical seen a similar type of, improvement based on the thing that we learned in quantum. So I think a lot of times, we're just at that point where it's just like, similar results, maybe a little bit better.
Okay.
And as with any model, classical or quantum, if you tend to just tinker with it to the point of, your loss and your loss for training and loss for validation sets are differing by a great degree, that can indicate overfitting.
Okay.
So yeah, it's the same issues, and I'll get to another one as well, because it describes, like, it's the same, like, optimizer costs, these types of things.
Mm-hmm.
So this is another COVID here too. So this is the second example that I found. And that, you see the one on the left is a classical. So those, coming from machine learning or in specific deep learning, convolutional pooling layers, these things are standard. Okay, you flatten, drop out. And then if you have a binary classification like this, you get positive or negative. Now, in the one on the right, you see pretty much the only, well, it changes a little bit at the end, but you know, it has some unitary in it, this 4-qubit circuit. And what I found with a lot of these is the size of the qubit circuit is most optimal as double the qubits for the number of classes. So if this is outputting COVID or normal, you're going to use a 4-qubit circuit. And it has to do with the inputs and the outputs and just the way that the model was constructed. So in that case, so you can kind of see what's going on, you know, different in the quantum model here with these medical images. So this particular paper, you know, this is 2021 as well. Like I said, there was a fair number of these that came out. So they're saying this HQ-CNN achieved an accuracy of 99% and 88.6, a sensitivity 99.3 and 88.7, right? So as researchers, the more that you can prove that they're similar fundamentally, and I'll get to some of the fundamental stuffs as far as algorithms and how data sets are actually mapped differently over a quantum bit as opposed to classical processing as well. So the third COVID paper, so I know at least one of these researchers here, it's a little bit smaller, so you can see data set size is just smaller. But what's interesting about it, it's basically distinguishing between influenza or the flu and COVID-19. But they, you know, it's muscle pain severity, temperature, and runny nose severity. So there's little bits and pieces that you can learn from a lot of these different ones. So they say the future work consists of fine-tuning our quantum-inspired model with more data inputs and multiple chosen features. So I'll get to a lot of this stuff as far as like, we're talking about the algorithm itself and how to get better performance and on a theoretical basis, and then run the model and then try to back it up every single way. Like, you know, we for sure, our model has better accuracy, but a lot of times you have to get like, you know, like kind of microscope the algorithm and these types of things. So this is a famous paper here. So this is an IBM Amgen paper. So for the algorithm here, so you can see this is 1, 2, 3, 4, 5 qubits. They only chose to show a portion of it, which is fine. I mean, you know, some don't show any, some show the upcoming. I'll show you some more algorithms upcoming here. But basically, anytime you're talking about real hardware and any type of like quantum machine learning or QiML, you know, workflow, you know, typically, you know, these types of graphs would be reserved for the ones with the simulators. So here's they also did a real, so you can see, I think this is about 25 to 30 qubits for this IBM Q Dublin. But this particular set, or this research, used a QSVM or quantum support vector machine, EHR data as opposed to images. And also with explainability, so XAI and as we know it, and chat values. So they touched on a lot of different things, and actually was fortunate enough to write a little review on this one. And, you know, it's just one of these that helped kind of get the ball rolling in like a bigger study, and especially with hardware too. Now, this particular one, so this is arthritis. That actually the IBM one was rheumatoid arthritis. So they're saying this is for precision knee QNN. So I think it's for arthritis in the knee. And there's nothing wrong with using these smaller quantum circuits. This is basically the HRY is the embedding. So this is where the classical goes into quantum data. And then the RX weight, this is the variational part of the single qubit. And there's hope of using single qubits because you get exponential, you know, increases in RAM and runtime if you have more and more qubits and more layers. So perhaps a better approach would, you know, stick with these smaller algorithms, but train them differently with different optimizers and, you know, have a better understanding of what's going on with data sets in the actual qubit. And some papers have, you know, touched on that. So they're saying for this one, our results need further research validation with larger real-world unstructured data sets and clinical validation with an AI clinical trial to test model efficacy, safety, clinical significance. So it's kind of like looking towards the future with a lot of this, as it should. And when I look at a lot of these papers, I see a lot of commonalities, like where these algorithms are based on a 2012 parameterized quantum circuit model that's meant for both especially for hardware. So it'd be interesting to see, the ones that aren't, basically not focusing on quantum noise and more like, hey, we have the physics, what's the best that we could do with this? So this next one is the last of the arthritis, my third example here. So these are hybrid quantum convolutional neural nets. And you can see here on the left, the quantum layer is here. I wanted to highlight, so Penny Lane and Qiskit, they both have these, and I previously focused on this, you can insert the quantum layer right in between other classical layers in existing torch environments or Hugging Face, but in specific, it's their torch connectors. Basically, that's what Qiskit calls it. Penny Lane calls it a torch layer. So it gives you that added functionality of having that algorithm, sandwiched in between somewhere in classical. And then you can see the second one here, quantum to classical transfer learning. So it just, we're going into 1, 2, 5 classes here. So like I said, a lot of these things, I found this kind of like, I just was experimenting, and that's what I found, like 4 qubits for two classes. And then my best one, performance and all, is 20 qubits for 10 classes. And I'll kind of show you some of that here. So regardless, this is most of their algorithm. So I just don't understand where it says angle encoding, because it's typically the H and then the first rotational gate, something like that. And then the random circuit here, and you'll hear this term random circuit is right here, and then it gets measured. Now, when it gets measured, it goes into bits again, so binary. So don't think of quantum like it's like this separate process for QiML or quantum-inspired machine learning. Look at it like, the software libraries like Qiskit and Penny Lane take care of the quantum stuff, and it all goes back into binary. That's just how it works. So this was in Frontiers, and this was this year. So this is another knee osteoarthritis. So it's important for these papers because there's working parts behind the data sets, and having these models, these hybrid classical quantum models, before we have even better understanding of the algorithms and in specific accuracies with that specific data set or new utilities. So they're claiming 98.36%. So most of these will compare to other classical models as well. So this next set is dementia. So they're similar in the way that they're, I believe these are transfer learning. It's a Penny Lane model. So they give you the full algorithm here. Now the resets, I don't believe you use, because you have the incoming elements from the data sets from some other ResNet layer. But HRY, and then this rest part, that's the embedding. And then this rest part is the variational circuit. And in case these RYs would more than likely be variational, meaning that the parameters are optimized over time. And this is what gives it the machine learning aspect of quantum, are these rotational gates right here. Are there any questions at this point? So we went through a couple of these different disease types with quantum algorithms. Are there questions at this point? And then they give another graphic here, and actually it was I think it was Ryan Kim, so implementing a hybrid quantum classical neural network by utilizing variational quantum circuit. Now, as far as the nomenclature and the names with a lot of these things, you'll see a lot of these longer type names. Most, if not all, are going to be these, quantum-inspired methods, just because the quantum computers have way too much noise. They don't do differentiation, at least as well as we could do with, this hybrid approach. And you can get exact expectation values, and your pure states are on the surface of the quantum bit, where, the quantum computers will be density functions, all, mapped within a certain sphere. And so they kind of break it down a little bit here. And then this right graphic tells you kind of like a pixel goes to a qubit, a pixel to qubit, pixel to qubit, pixel to qubit in these cases. And, this is the embedding layer. So the Hadamard gate, superpositioning, the rotational gate, turns it, I think it's 180 in this case if it's not parameterized, and this other part is variational. So I wouldn't be surprised if we get a new variational circuit sometime coming up, or at least a lot better optimization or optimizer approaches to, say, like freezing certain of these layers in quantum, similar to deep learning nets, or doing some other modifications throughout the course of the run. You could drop out layers, and some of these things you can do right now. But the tricky thing is if you're like NumPy, PyTorch, and PennyLane, then you have to, like, your optimizer has to be this one and your loss. So everything has to be correct in the code, in other words. And then I wanted to show you here. So this one shows the output, cost, and optimizer. So like I said before, in quantum with the libraries is they calculate the exact outputs, and it's in binary. And then it's the same thing in classical. You still have cost function and an optimizer. And then so it gets trickier if you're trying to do like a ResNet, neural network and the quantum variational circuit at the same time. These methods will likely be improved. And, say we have NumPy quantum specific optimizers, but I think at PyTorch, they're just like for the whole hybrid network. So, it should definitely get there. And then this was another one too. So this is actually a different set of researchers, but you can see they chose to use more layers in this specific one. So still the HRY embedding, and then 6 layers of and this should be trainable for these RYs. But keep in mind, trainability adds, compute costs, and more layers do too. So in this case, if it's binary classification, you'll see these 4 qubits for the 2 classes coming out. And that's represented by demented and not demented for this specific data set. Any questions at this point? So this is the second dementia one, and I've previously featured these as well. And if in an ideal world, the PennyLane and the Qiskit simulator should be the exact results, but in this case, you have compilations. So basically, these circuits that you or I would design aren't usually the same as what the machine, interprets them as. So I think that's the main thing here. And there could be other subtleties in the notebooks, just the way the code is written, as far as the PennyLane being higher in this specific one. So, I did a similar study. So they said when their quantum depth 6, which is represented by these 6 here, that was the max accuracy, and that's why they're showing in this specific one. So this one would be a little bit harder to run, on, a default.qubit, lightning.gpu, which is a NVIDIA GPU quantum simulators could make short work of this if it's compatible with the notebook. And they said they got 92% with this for this particular one. So I think this is a Kaggle. This is a Kaggle data set. And this third one for dementia, this is using ADNI. So this is probably a harder data set, or maybe even bigger. And you can see this particular algorithm. So what's interesting here is it's similar to the previous 2 dementias, but in this case, the CNOT gate, this is not, there's anti-controls, there's different types of, but this would actually be, anyways, there's different ways of running circuits. So I'm not sure if that's just something they did, or something that got changed, or if it's the same as the other, or similar to the other 2, but that's just worth noting with that particular target. And then you can see this is what they said they got. So for Parkinson's, 97%, for Alzheimer's, 96%. And again, as with everybody, the most important thing is on the algorithm basis, even if we're losing, speed on the input and the output of the classical data going back into classical from quantum, it does theoretically make sense. And I think this is where physics comes in, and, does the data set, with this specific circuit, was it designed to separate 2 different data sets on opposite sides of the block sphere or the qubit for that one. And this was 2023 in mathematics. And then they give a brief overview here as far as the output. It's binary classification. And then any questions at this point as far as anything, the medical or the quantum? at this stage of these papers, for medical R&D. And then, so this paper is currently not available free. I was able to get this before. It's a 4-class classification. So they actually did use 4 classes. They might have, I think this is the convolutional neural network as well. Some of the diagrams will give away as far as where they get the demo from. So basically, this is one of the higher ones for multi-class classification. Binary is a lot simpler than, anything beyond binary. And then the more classes you get, especially if you're limited in specific images and specific directories or, for that class, you're not going to likely get as high of values. So they said they got 97.8% with this particular one. And I like this paper. I've read this paper, and they give you the overflow here. This is actually for the classical one. So the quantum one, insert the circuit. Now the quantum circuit doesn't always have to come after the neural network. I've seen it in the literature, both before and after. And as far as I know, I think you can run multiple quantum circuits in future notebooks, different spots. I think the issue now is just trying to understand better where the placement of the single one is. And same thing with devices. You could have like this specific simulator or this hardware for this application. And here's the second tumor one. So they call it 3D quantum-inspired self-supervised tensor neural network. So this is not a convolutional neural network. Now, there's advantages in basically with quantum variational algorithm simulators or simulations, is that you can go higher in qubits with tensor networks. Like NVIDIA got up to like 1,100, 1,200 qubits with like 700-800 GPUs, for GPU quantum simulators. But you typically can't do as much entanglement, those types of things. So you're basically relying a lot on these trainable parameters from the rotational gates. So you'll see this. So this is Konar D et al. In 2023. Now, as far as the repositories go, just be a little careful because they can update them throughout the years. I've seen it updated for like, typically between 1 and 2 years. They'll just update it, whereas like the nature and the science and these types are typically, once they're in, no more updates. And a lot of times they'll do an analogous one. They'll do the archive with the nature, those types of things. But TechRxiv, I think, is IEEE. And this is a segmentation paper. So 3D-QNet has achieved promising dice similarity as compared to the time-insensitive supervised convolutional neural network-based models like 3D-UNet and others, okay? And then this next one is a bunch of the research for the startup here. So what I did in these is that I took 2 different, so ResNet 18, I think it's maybe 11 million parameters. And then the VIT is a vision transformer. It's more cutting edge. We're seeing more transformers in medical. There's already reviews on them. And I used a 44 class data set. Now, this data set was good because it didn't have some other brain images. They'll show a different, size, sagittal view and cross section and all these types. And you don't really want that unless you can represent each of those views correctly in your training data. So that's the data set that was used in this particular study. And what comes out of this is the 512 elements. Now, this is similar to, say, the dementia studies. If they use ResNet 18, you're going to get 512. And then this particular one, Vision Transformer 768. Now, what differs between all of these, and especially, these first 2, is that the way that the model was set up and, some difficulties getting, I haven't seen too many other people be able to train the classical neural network like a ResNet effectively at the same time as a quantum circuit. And in this case, the only thing I would run with 4,400 images is 20 qubits of 2 gates, okay? So this was my go-to for a lot of the experiments that I ran. This looks like, the Golden Gate Bridge in San Francisco, as some may say. So as you can see here, it's the embedding layer. And what's unique about this HRY is its output is it's a sine wave. And now the sine wave represents the surface area of a qubit. So I think there's something, this one typically ran a lot better than other embeddings. And I did do some training layers and other experiments that I did get better results with more and more layers, but it wasn't like immediately obvious I had to really work at it, basically. So using this HRY, I did 2 class, 4 class, 10 class. This is 44. Like I said, the 10 class worked the best because it had the most images per class. And I saw the best response to adding more, quantum layers with that specific data set. So the validation accuracy, 63%. And then this compared to the classical model of 58%. The main difference is this has the quantum circuit, this does not. In both cases, the ResNet or the classical neural network does not train. Now, in these bottom two, this was a really good model. So this C, so 85.2%, and this is all ResNet layers are updated. They call it fine tuning, right? So you have a pre-trained network like ImageNet. Now you're doing fine tuning. Now then this last one, this transformer model, I tried to get with a quantum circuit, and I don't think the quantum circuit worked at all. I had an issue with the confusion matrix, which plots out 44 by 44, and that one didn't work. But 82.8% kind of gives like an idea of where, the transformers was in this. There's also been cost efficiency studies, algorithm prototypings, device benchmarking, parameter optimization is basically I kept adding layers to the HRY. And at 8 layers, I was able to confirm today that it is better than just the embedding, with HRY and other data set sizes. So moving forward here, so there's a cool quote by Michelle Thompson, and she's at University of Pittsburgh Medical Center. AI has allowed me as a physician to be 100% present with my patients. So it's opened up a lot of stuff, and organizations and universities like Stanford, 110% behind AI as long as it's done well, these types of things. So, like I said, like these algorithms, this model was designed for noisy hardware, right? So we're in QiML, quantum inspired machine learning. So we don't have noisy hardware, we can get exact answers, these types of things. So what it looks like is going on here, and I mentioned this before, is like NumPy, especially in PennyLane, they have like 6 different quantum specific optimizers. So these are the things that take all of the weights, typically, well, it just depends on the model. This could be quantum or classical. And then they change them over the course of time, your run in your notebook to get the best, rotation angles on the qubits. So there's quantum specific optimizers I haven't got into quite yet. And you can also, one of the researchers at PennyLane said you can actually take the quantum circuit and then, keep unfreezing layers throughout it. So that's something like, it's very, very deep learning, like in these approaches. So these are, for instance, 2 of the optimizers, the NumPy optimizers in PennyLane. Now, the issue I have is because I have PyTorch optimizers in a lot of these notebooks, and there's NumPy, and then, which one to, how to get a loss function that you want in this, framework, and then your cost function in another, I still have to uncover, but this is where the industry is likely going. And like I said, like the very first thing anybody should do, especially if doing like classification models, is only run the embedding. Like the HRY, it just makes sense because it's, like its output is the surface area of a qubit or the block sphere. And then do some layer studies before just throwing in random, quantum circuits or quantum circuits that, you haven't thought of much of. So then increase the layers, your depth, 1 layer, 2 layer, 3 layer, maybe all the way up to 10. And most models will run, on CPUs and GPUs like that without using too much RAM. But like I said, like, I was able today to get this as far as like, 8 layers of this rotational RY gate, plus the embedding, better accuracy, however, a lot slower, as opposed to just the embedding. So just start with the embedding and see what you get, and then start adding variational layers, because it is possible to get even greater performance. Now, this next section here, this is basically at the time they called this training the embedding, and they've kind of let off the gas with this whole term, because it could be causing great accuracies, but overfitting. But there's a lot to learn in this paper, especially they say linear decision boundary in the 2D Hilbert space, which is representation of the qubit, corresponds to two linear decision boundaries in the original space. So you want to have one data set, if it's binary, on one side of the qubit, all of those map there, and on the complete opposite, the other one. Now, this has been done by Kristen Temme at IBM. Like I said, Seth Lloyd, Maria Schuld, and forget her first name, but IJES basically. And then this last one, so train feature map embeds the data into tight and linearly separable clusters on the block sphere. So if we don't know what's going on, and they've actually made quantum circuits just for specific data sets, but if we don't understand what's going on between, the interplay between the qubit and large data sets, then it's no good, like that's important. And, so you just have to read a lot of these papers, I would say. Are there any questions, any slides in particular that anybody has questions on? Yeah, so, there's a lot of research to do, but it's almost like, don't take things like, not for granted, but like, like you always want to be asking questions. Like if they say like in an article, like this QiML article, that pretty much everybody, is getting just marginal increases at best, there's something with the algorithm, or like, the processing between, the classical data to quantum, these types of things, right? So it does help to ask questions in forums, and you can ask questions in Penny Lane and Qiskit. There's also, I think, a small one for Google Circ, those types of things. I saw a number of people come on here, and it's definitely fun and exciting. I would definitely, if you're trying to build your repertoire, do some benchmarkings between different GPUs and CPUs. That's a study. And then do another one adding layers to a good, existing circuit to see, which number of basically quantum parameters is optimal. That's a good study too. And then the other thing, it's a business, right? Like, so you could take runtime, and then with your knowledge of the, like, say, collab rates, if it's like $1.30 for their top GPU per hour, you times that per, hours of runtime to get cost. And then efficiency is just 1 over cost times time. So that's an efficiency study right there. But yeah, I would definitely go through the motions, just like a lot of these papers do. I mean, I don't think too many people were expecting quantum, machine learning, or, this with simulators right out of the bat would be awesome performance right away. But I think a lot of this, like, we just need a next gen, and especially like optimizers, those types of things. Like it just seems like a lot of things are just like, I can run hundreds of different algorithms, right? And then I don't get that like separation that you would expect with a quantum bit with exponentially large feature spaces versus classical. And then any questions? So I saw some people hop on. So Ron or Dave? Yeah, go ahead, Dave.
No, Ron just asked what's QiML, and it's quantum inspired ML. And yes, you did say that, Captain.
Yeah, so over these past several weeks, I've been digging up a lot of the literature, and there's 3 or 4 main benefits, right? So number one is no quantum noise. So if you have any quantum noise, you can't do pure states, okay? So if you do pure states, that allows you to map data on the surface of the qubit, not on the interior. So that's a big one. So another thing with hardware, and I'll have to do more research in this, but as far as I heard so far, is all of them you have to do probabilities. So you have to do, like, every time you want an answer, like, if you want a really good answer, 10,000 shots, 100,000 shots, those types of things. Now with a simulator, you just calculate the answer for the circuit, and you could do an exact expectation value, which is the exact value. And this is needed every time you analyze the circuit. So if you have a machine learning workflow with 100 images and 10 mini batches, that circuit needs to produce that exact value 10 times, right? So 10 times 10. And as far as the other stuff, I haven't heard anything else as far as hardware. So parameter shift differentiation is hardware friendly, but they've done studies and your runtime with number of parameters goes up exponentially. Whereas if with QiML or quantum inspired, it just goes up slightly, like very slightly. So like it's similar to back propagation for deep learning, but with quantum circuits. So those are the three big ones, I would say. And anybody else that we haven't heard from? So Peter or Dino? And I think, and just, based on what's in the chat right now, Dave, if you have any other questions too, is that like, why is this such a big thing? Why is, quantum inspired machine learning, why is that such a huge thing? Is because it works, right? Today it works because of those three factors. And then our understanding of data sets and qubits and processing needs to get better and implemented better. But, this QiML or quantum inspired machine learning has been used for, you saw from the papers, at least 2021, 2020, somewhere around there. And if you're talking full workloads, and we find these killer apps for quantum, how can we use the circuit? Is it before the neural network? Is it after? Did it just like alleviate a bunch of stress from the neural network that now, the quantum can do quickly just because the quantum algorithm can? So, those types of things, needs further, I would say, pinpointing. And, it's just waiting for the next generations of anything in emerging technology. But I would say that the results, that I presented today on these, like 9 or 12 different papers, they're all very encouraging. And the framework, like what they had to do to get the data right and the algorithm, and think like, okay, now we have a better optimizing method for the circuit, and you don't have to change your notebook too much. Like that's the type of stuff that I see coming. And then Dave, did you have anything else?
No, just as always, thank you, Kevin.
Yeah, you're welcome. And, stick with it. And the other thing is quantum machine learning, and I think this is mostly QiML at this point, is predicted to be the primary application, $5 billion by the end of the 2030. So we'll likely see some developments, but that's, if people are crazy about machine learning and deep learning like they are today, just imagine like there's a quantum circuit that runs well in an existing model without much change, and all of a sudden it's just like new industry. Awesome. Anybody else that we haven't heard from? And I know, a lot of people have, done extreme algorithm studies, and this is awesome. And, it's application in everything. I don't think there's any algorithm that just runs by itself. I think most require, hybrid notebooks, and there's a good chance that the other classical part could be, this machine learning or deep learning that's doing a big thing too. So I think there's also a question here as far as, you don't need as many qubits, those types of things compared to bits. And I'm kind of seeing that too. So number of parameters in QiML or quantum inspired machine learning is set by basically these rotational gates. That's it. So you can have an Rx gate, which it rotates around the X axis of the qubit, and Ry and Rz. And over the course of the run, so if you say you have like 2 in a row, like one layer of the second ray, this could be returning, spinning at 0.67. This could be at like, 0.9. And those get optimized, right? So the more layers you have and the more qubits that you have, the more parameters that you have for potential optimization. Now, if you caught the earlier part, and for those that weren't there at that time, if you have a 2-class classification for a lot of these models, that requires a 4-qubit circuit, okay? So it's 2 to 1, so qubits to classes. And I saw this for 10 classes, and I couldn't get to 88 qubits because penny languages is like 30. But I could get for 10, right? I could go 20 qubits for 10, and the accuracies were, how would I put this, better, than the surrounding qubits if I chose 18 or 16, or, for this amount of data, I couldn't go higher than 20. So that was a good one that worked for me because the data set had a lot of images per class. And when I kept adding layers, like 8 layers of rotational gates, then in specific, that one had the best accuracy. And now I could potentially take that into other different models too, or at least the theory behind it. But what I've heard in industry is if you have several different data sets, you need to have different algorithms, or at least an algorithm. This is contextuality, or those inductive bias. But with my 10 and my 44, my 10, because it had more images per class and because it had less classes, it responded the best to an increased number of parameters or layers of the variational circuit. So, I reran it and, again, against the just embedding, and the embedding is a lot faster, but the results, this HRYE, aren't, the accuracy wasn't as good. So yeah, anybody that wants to get started, definitely just find a good embedding like HRY, something like that. And there's different combinations of it too. And then just keep running to find the very best embedding. And then, keep adding variational layers, at least our rotational gates that get optimized over the course of the run. CNOT gates tend to not, for these applications and classification that I found, been too helpful, and they use a lot of memory as well. So you'll see these other studies, they couldn't get up to 20 qubits and 4,000 images, those types of things with CNOT gates and things that typically didn't help accuracies in those models. So yeah, it's specific, depending on the problem, right? As far as like what gates you actually really need, what gates just chew up RAM and time as well. Go ahead, Ron.
Hey, Kevin. I hate it when I join a meeting and a phone call comes in. But I did want to ask a question about you've gone through so many tutorials. I know there are some where they reference turning a medical image, like from a scan, into encoding it directly into a quantum register, as opposed to having a quantum layer embedded in the stack, where it's just reading outputs from one layer and processing them and then sending its response to the next layer. But in the case of the imaging, do you feel like these tutorials give a good dissertation on how they encode the image into a quantum register? Do they take advantage of the the hyperdense encoding feature of quantum?
Well, like I said,
or is it just a function they tell you to call?
Yeah, this whole pixel per qubit thing, that I think we're in 2 of these that I showed today. And I've seen that before, right? Like you can just, whatever's coming input, it's just like, 4 pixels at a time going through 4 qubits. That's what I saw for that. Now, as far as the data sets go, I will say that Google Circ did the study with stilted quantum data sets. It actually might have been TensorFlow Quantum. Anyways, they're both Google. And they took an MNIST data set, which is standard, just digits. And, I believe it's running like a quantum data set. So as far as medical images running like that, like you're prepping this before, so it's you don't have to get embedded. Like quantum chemistry has, PennyLane has it. Qiskit's renamed it to Nature. It's no longer, chemistry. But there's all these, quantum data sets too for chemistry. So yeah, as far as the exact form and function, I'm not quite sure. If you have these thousands of images, turn it into stilted quantum data sets or some equivalent that you're now can access them without embedding. That'll be interesting. But I get your question because so if you don't do embeddings, a lot of times you're saving time and you can actually get better performance too. And this is a goal for the industry, is to get to quantum data. So it's worth a lot more research to see what can be done with existing classical data sets to turn them into, for lack of better terms, pseudo quantum data sets, and then using that directly as instead of classical to quantum. Anybody else? Dave, you have any questions?
Yeah. So you were saying you're running these yourself. Did you download the software, or what did you
Yeah,
get the
so
code?
this question comes up a lot. So it's all based on these .ipynb notebooks. So that's where you start. Okay, so Qiskit, PennyLane. The Qiskit ones, they'll typically you have to go to GitHub, and then just right click raw and then save file as. The PennyLanes are on the right side of all these demos. So QML demos, or they probably have they have over 100 other demos. And then once you get the .ipynbs, you can run this on a local Jupyter lab, or you can run this in Colab, which is what I do because I need the GPUs. There's a million ways of running. So that's the standard, right? So, I'll get trying to think what the question was before, but basically this is your progress. So when you run and you get your results, like in Colab, I do two things. I print as a PDF, and then I click file, and then I download the actual IPYNB, which is essentially like a text file. So the PDFs are easy to access because you could just scroll through like a PDF. Now the text files, there's a lot of other, code in there that you might not want to see, but you can always hit like control find and find it inside notebooks. Were you trying to do anything else, Dave?
No, I was just wondering what you were doing.
Yeah, so that's the standard approach. And like I said, I did 26 of the PennyLane demos, improve most of them, and then, modified them all. So it's good to practice. So change CZs for CNOTs, these types of things, double the qubits, double the layers. There's different options for basic entangling layer. There's different templates. And it's worth the time because languages, tend to be more universal than other areas of research. And it's good to know the fundamentals behind quantum and all this stuff. But, you're not going to likely run much into adjoint differentiation, which is like a key, if the notebook will run it, of doing just like backpropagation, but for quantum and classical layers. So yeah, it's worth the time, become an expert in a language.
So like for Xanadu, you just grab their notebooks using the PennyLane framework, and you download them and just upload them into Colab, or do you log into Xanadu and use their
No, they're all
platform
open
specific
source. So
Yeah.
if I type in PennyLane.ai, the key things are you're not going to be able to understand everything about these notebooks unless you go through documentation. So they have a section, it's called Using PennyLane. And then they have quantum circuits, gradients and training, quantum operators, just like Qiskit, like how you'd go through that, these types of trainings.
So have you run through the exercise of actually using the Xanadu backend from
I've
Colab? You have,
I've
you have to,
researched it to try to help people. So this is Strawberry Fields. It's their photonic processor.
yeah,
And I know the one they had Quantum Advantage on. So quantum advantages are typically for very specific tasks. I think they shut down the Borealis. That was like their big 216 squeeze. They call them modes, for those types of things. So
I assume they have something similar to what IBM has. If you have an account with Xanadu, you can grab an API key and install it in your notebook, even if you run it from Colab in the.
yeah.
And
There
then
was
using that API key, it'll be able to link it to your account over in Xanadu and run it on their hardware.
yeah.
Um, I just wondering if you had tried to do that.
Yeah,
with
I
any of the
haven't
tutorials.
like personally run, experiments with that, but there's people that get on and it's just a simple fix. Like a lot of some of these things, like if you do Penny Lane and Qiskit or Penny Lane and Strawberry Fields, the install is like pip install, and it'll say like Penny Lane SF plugin, which gets you both Penny Lane plus SF in one
Yeah.
pip. Same thing with Qiskit. It's Penny Lane, pip install Penny Lane Qiskit. And so you don't have to install Qiskit, then Penny Lane, those types of things. But yeah, you should get on the forums, the Xanadu forums, because there's a fair number of people on these smaller photonic, like 8 mode, processors. And a lot of it's just, they're more simple questions. They're like, this doesn't work because they didn't install something.
Yeah, so the Penny Lane dash Qiskit module that's the interface module. So you can write your applications in Qiskit and you can ship them out to Xanadu's Strawberry Fields backend just by using that interface framework.
Well,
And again, I guess you have to put some sort of key in there so it knows who you are and whether your account is active and all that crap. So
yeah, the Qiskit, what is that called? Like your token ID, that type of stuff. Yeah, so if you're trying to access Qiskit hardware in a non-Qiskit notebook, so this is like Colab or local Jupyter Lab, you have to give it your token ID. And these shouldn't be too many lines of code.
yeah, I mean, a number of the platforms support Qiskit as an input language, and you don't, just because you write something in Qiskit doesn't mean you have to run it on IBM. Anybody that has one of those transfer modules will allow you to write your program in Qiskit and then send it to their hardware. I think that's what you're talking about. You install the Penny Lane dash Qiskit. It isn't 2 modules. It's just that one interface package.
Yeah, I mean, they got a whole demo using Penny Lane and IBM's quantum devices and Qiskit here. So yes, Penny Lane is probably out of the bunch, maybe one of the leaders as far as trying to keep everything as open source. Like they have, I mean, as far as they have JAX, they have TensorFlow. Qiskit, I think, just has Torch, as far as QiML or quantum inspired machine learning. So this is their thing, right? And you can access hardware and this type of stuff. There was a really cool demo. It's called Ensemble Learning. So you pick 2 different devices, and it could be for like Rigetti and Qiskit, or it could be like, Penny Lane and Circ, Circ.qsim, something like that. And then they're both classifying images at that same time. And then it gives the specs, and they say this specific device, did a better job recognizing, how does it put it? If it's like an iris data set, like this aspect of, this class of iris, for this device. And you can, based on all this like installs and, plugins, is that you can incorporate all these different features from Quill, which is Rigetti or PyQuil. And same thing with like circ.qsim. There's a number of demos that are, circ simulators penny lane code. And actually, it's that circ.qsim is the code for penny lane for the circ for the Google circ qsim. That they don't call it that. Penny lane calls it that.
Well, it's cool. You can get a lot of testing done with the standard simulators.
Yeah, and so Peter asked a question. I found one circ. I don't remember the name of the. It's not Slack and it's not others. It's like a green logo, but I don't know. I didn't get too much. I tried opening up, sharing research, these types of things. So it should still exist. I mean, circ is just for algorithms, right? It doesn't have all this ML stuff that PennyLane and Qiskit has, right? So circ depends on TensorFlow quantum, and then you also sometimes need TensorFlow or Keras, right? So yeah,
Well,
you're
yeah,
basically writing circuits.
Keras is a front end for TensorFlow. You have to use them
Yeah.
in tandem. So I would say to the person asking about circ, try searching for it on Discord or Slack. I bet there's a channel or two over in those areas.
Yeah, and they've had some recent tutorials, I think even this year, like it's Google Quantum AI. Okay. So Google Quantum AI has circ, TensorFlow Quantum, TensorFlow, Keras, those types of things. And Google Quantum AI still puts on it seems like a pretty decent effort. It's just they had quantum supremacy back in, this paper was like October 2019. And they keep making improvements to the 53 qubit, Sycamore processor, but it's not like they haven't, released it. I don't think they've released any hardware after that. So things are basically waiting for the next breakthrough, maybe over there. But there's a decent number of like I said, you're going to have to go to TensorFlow Quantum to do differentiation and all this stuff that PennyLane can do. And I don't think you can write your own circuits with TensorFlow quantum. It's different than some of the other ones.
Well, you can do a lot of work with TensorFlow by itself. It's tedious. You're much better with something that runs in front of it, like Keras, like you were saying. You can actually also get PyTorch to use TensorFlow as a backend. But I think PyTorch has alternates too. But if you're doing something big and you need to work in a distributed area where you need more than one core or one machine or one GPU, you're crazy not to use TensorFlow as your backend.
Yeah. So another breakthrough is going to be if you can get these CPU quantum simulators to run multi-threaded, like if Circ's, this QSIM simulator is 90 cores with Xeon. If you can find a way to, and I haven't seen anything yet, to run 90 threads, your performance might be bumping up against some of like a single GPU quantum simulator, and it's free, right? So circ.qsim is no charge, whereas you're going to be paying somehow for the GPU, quantum simulators. So, there's different ways. I don't know, like Ron, if you know, like OMP, or was it OMP, OPM? No, it's OMP. Open. Anyways, it's in a lot of notebooks, and you could do multi-threading. So you set threads is equal to that. But for me, I still have to figure out, like, is that for the notebook? Because sometimes you have to do a bash script and export it into Python, your Python, this hybrid quantum notebook. And, that's how you can get, there's a simulator called Kulax. I know for sure you can do multi-threading with Kulax by using bash, which is not a direct approach. So I still have to learn that one too,
I can help you out with bash. No worries.
Yeah,
Sounds
so
like fun.
yeah, some of them are in documentation. Some you learn a lot from the demo, from the like say the Qiskit forum seems more users, but a ton of users, like all over the world. Now the Penny Lane ones are actually Penny Lane researchers. Like they just go on to answer people's questions, usually within a day or two, except for on the weekends. So, you know, you'll hear things like, okay, like lightning.qubit did not have multi-threads. Now it does, but I can't find that. And they have, you know, lightning.cocos, which nobody really knows about because it's not part of the plugins page. So, you know, you just, anyways, when you get to the discussion forum, just search in that search thing and then open the first 5 or something. And then a lot of times you can find your question on previous answers. Yeah. So Peter, and feel free to come on, but yes, it's QQuantum for CUDA Quantum. And then there's CODA for QODA, and that's for the hardware, quantum hardware plus classical hardware, you know, no, you know, QiML in this case. So NVIDIA's QQuantum is now parallel, yeah, but it's a new language. I don't know if you could talk more about the NVQ++. I know that you can do multi-node, and this is through a function called MPI. So you do that, and then Brookhaven National Labs doing it for us, and I think for them too, even if they're doing like, say if they're doing over 200, is it 200 qubits? For us, you know, for Penny Lane for consumers, I think we're like 30 qubits, you know, GPU quantum simulators. That's the max right now. But they're, you know, no quantum noise. So, but I haven't heard about this NVQ++, Peter. Yeah, here's CODA. So Peter put in the chat there. Yeah, I've seen this before. Okay, NVQ++ is between QQuantum and the GPUs. So there's a lot of hope for that. Now there's a little trick. I'll put it in the chat here. So in order to get to an NVIDIA GPU, you can actually just go through Colab and select like a V100 or A100. And with the correct pip install, it recognizes that you're paying. And then you have access to, I believe, a single GPU. And you're paying for $130 for like an A100 an hour, you know, say for instance. So yeah, sometimes you have to get the right installs for a lot of these things. Any other questions? Questions or comments? And I would say, you know, with the news, like the Brookhaven, Penny Lane, NVIDIA, and I think there's 1 or 2 other ones, NERSC, something like that, that they say 6 more of their big, you know, GPU quantum simulator experiments, you know, the rest of this year. Here's a Tom's Hardware article, and it said that GPU quantum simulators will outstrip, you know, quantum computers for a while. So nobody knows the exact time, but keep in mind, there could be quantum hardware breakthroughs that they don't necessarily have to fix things or, you know, satisfy all 3 of the conditions I say that QiML has, you know, with pure states and exact values, these types of things. But there could be a breakthrough that you could do differentiation similar to like, you know, classical, and that might be worth researching too. Awesome. Any other last questions or comments? You know, just don't give up and run experiments. I put that the Penny Lane demo in the chat. So yeah, just open one. If you like graph embedding or GANs, you know, QGANs, everything's quantum, or there's some aspect of quantum to it. Just find some demos and just find a way to run them. A collab is a lot easier than setting up, in my opinion, your own Anaconda. Jupyter Lab and Jupyter Notebook are somewhat easy, but I've had issues with compatibility. Anything, Dave?
Nope. Just thank you. Have a good one.
Yeah, I appreciate everybody come on. So again, this has been discussion 102 for September 28th, 2023, specific QiML algorithms for medical R&D applications. Have a good night, everybody, and have a great rest of the week. Take care.